ready to start?
Yeah.
Okay, perfect. So we did part A, question 1, and BT did the work, so I'm going to explain the question. So this question asks us to get the rate of change of a vector with respect to time, and then the time that we are going to solve that derivative is at 2.8 seconds.
Okay.
So this is a temporal vector derivative, because d over dt. So we start with the vector of L equals a I hat plus b t squared j hat plus c t k hat. So basically this just means that we have a in the I direction, b t squared in the j direction, and c t in the k direction because I, j, and k are both unit vectors. So when we derive it in respect to time. So the derivative will leave us with 0 in the I direction. By getting the derivative, we get 2bt in the j direction and c in the k direction. So after that, we plug in 2.8 for t, and we also were given different informations for b and c, which should be here on the slide. So b is 4.7 kilograms meters per second cubed, and c is negative 7.9 kilograms meters per second squared. So when we plug all of that in, we are left with a vector of 0 in the I direction, 26.32 in the j direction, and negative 7.9 in the k direction. And this is all meters per second squared. However, it asks for the magnitude, so we have to make it a scalar. So by doing so, we take each one of these squared, and then we take the square root of that. So the magnitude of L with respect to time of the rate of change at time t 2.8 seconds, we get 27.48 meters per second squared.
Okay. So the procedure is perfectly right, and I'm glad you also mentioned the unit vectors and trying to explain the process. But just a few things which might improvise this whole thing. One is we will be using this prime for derivatives with respect to s. Of course, you're not aware of this only. And so any derivative with respect to t, we will, exactly. So dot is what you would like to have. And also in terms of the what you put on the left hand side on the top, so that's not with respect to what the derivative is taken, but with respect to which frame of reference the derivative is taken. Okay, so that happens to be in this case the frame in which your I, j, k are all fixed. Okay, because that's why you are able to just take the derivative of a and say it's 0. Otherwise, this term would have led you to this term plus an a I dot, and which would have been non-zero. Similarly, a j dot and a k dot terms would have come. So this is not just for them, but for everybody, for the remaining problems today as well as the rest of the course, the other homeworks. I would like you to start every problem with drawing a frame of reference. Okay, so just draw a triad. Go ahead, yeah. Just draw a triad, I, j, k, the unit vectors. Yeah, perfect. Yeah, so you can mark them, I, j, and k.
Are they just, they're just
Yeah, you can put k hat. Yeah, okay. That's a good practice as well, because all unit vectors we typically say is hatted, so that it's understood that its magnitude is 1 without saying that. So that's the idea. So once you have that, so always start with this frame of reference and the coordinate system. So in this case, the coordinate system is obviously associated with the whatever is the coefficient of I, j, and k. That's what you have going there. It's not necessary to calculate this, what is asked of this question, but just I'm talking about certain good practices. If you have much more complex problems can be easily tackled, so that you have a systematic way of approaching the whole problem. Okay, so now you call that frame, you could give it some name, say I, which is the inner uppercase I, and always frames of reference we will denote with a circle around it. Just like unit vectors we are denoting with a hat, we will denote the frames of reference with a circle. That could also be a body sometimes, like the aircraft or something, earth, whatever. So this I, so now you can replace these t's, superscript pre, superscript t with the I. So yeah, and exactly. Perfect. Yeah. So certain things I'd like to appreciate, and I would like everybody else to replicate as well, is the fact that they used units with every quantity that they mentioned, which is very important, because then because sometimes units could be given in a mixed way. In this case, everything is in SI unit, so not an issue. But sometimes units, I'll come to you. So sometimes units might be mixed, and therefore you'll know when to make conversions and things like that. So it's always a good practice to follow the units throughout. Yeah. In this case, of course, it's not mentioned specifically, but we'll be using, because I'm using this as a learning process for the classes as well. L is a symbol that we typically use for the translational momentum. So it's the mass times the velocity, the translational velocity. So typically that will be given in terms of the mass, which is kilograms times meter per second, which is why you would see the units are this way, right? Kilogram meter per second, because the first one is just A, so you can see that. Whereas the second is multiplying t squared, so 2 times time will go away, second squared will go away. Once again, it is kilogram meter per second, and here 1 second will go away because 1 t is multiplying here. So that will also be in kilogram meter per second. And this quantity that we're talking about, the rate of change of the vector L, is also very, very critical, because as you know from Newton's second law, the rate of change of translational momentum is the force. So whatever force you're applying is what causes that momentum to change, and which is why these will have the units of the force. Okay, so which is why this is not appropriate. So if you can just correct that. So start with so each line, if you write the units, then it will be okay. So L is having the same unit as A, which is kilogram meter per second. So you can write that on the first line of the equation that you have. That's in kilogram meter per second. Okay. Okay. Now, when you're taking the derivative, what happens? You're taking first derivative, right? So 1 second will come in the denominator. So that's what you would have here, and that would continue all the way down to the last line.
I have one question about.
I'll come to you.
So if we were to have like non-zero vectors for non-zero derivatives for I, J, and K, how we would notate that? Because I know the derivative of I hat, J hat, K hat would be like I hat dot and like J hat
Correct.
dot. But if we had to expand it out, I just wanted to know how we would notate that.
Yeah. So a very good question. We have not yet gotten there, but in fact we did not for the Cartesian coordinate system, but remember we took up the polar coordinate system and extended it for 3D to cylindrical coordinate system. There we had this ER and E theta, which were changing with respect to time because they were changing with respect to theta. Okay, so we did derive that. In fact, I'll probably revise that because we went through a little fast towards the previous afternoon. So I'll just try to look through that so you can understand how it is done. So the whole idea is you have to take ijk's derivative with respect to a particular frame. Okay, so if it happens to be instead of I some other frame with respect to which you're taking that derivative, then you have to know how I moves with respect to that frame. Suppose I call that E. How does I move with respect to E? So only then you will know how to take the derivatives. And we'll introduce another concept called the angular velocity vector today. So that will become a tool with which you don't need to actually take derivatives. You don't need to use calculus. You can just use a cross product from linear algebra. So it's an equivalent of taking a derivative, and we will see that. So I'm telling a few things ahead of what we have already learned. So obviously you would know, unless you have studied yourself, you wouldn't know about these things. That's fine. So, but I'm using this as a part of the learning process. So, yeah, did I answer your question?
Yes. Yes. I'm guessing.
So how to get the I dots? Yeah. But we have done that one example where ER dot and E theta dot were calculated. We will go back to that. Yes.
So L dot is the derivative of L with respect to time, which is appropriate in this case. Can you explain what the prime notation, how that's different and why that's not appropriate?
Very good. Yeah. So let me just, good that you have two colors today. So just let's say, I think I preempted myself as the curse of the speaker. So let's say you have a curved path like this. Remember that We also talked about even simpler thing where we had it on a straight line, what we call as a rectilinear and a curvilinear path. Because remember, as of now, we are still talking of particles. We're not talking of a body which is rotating. So it's just a particle motion. So the simplest thing was we started with s is equal to 0 on this, and we said that s goes on this particular line. So it's a derivative with respect to that s that we will denote as primes. But s in turn, remember, is a function of time. Okay. So any derivative with respect to, let's say, take the same vector, for example. So another important thing is, of course, I see that you have overwritten this to make it bold, Gracie and Witty. But I would prefer when you're writing on a board or to use either an underline or a arrow on top. Okay. So either you can use this or this, one of them, right? Not both. Okay. So, so the same thing with L dot, because it remains a vector, right? So it's important. That's another good practice to always keep in mind. Okay. So I really request for the other 6 questions also today, for all of you to follow this. I do not want to keep repeating the same things. Okay. So coming back to prime. So prime would be, for example, if you're talking of L, it would be a derivative of L with respect to s. We will denote it as L prime. Once again, of course, these are vectors, and whenever you have vectors derivative, you will mention the frame of reference. Okay. So with respect to the frame of reference I, you're taking the derivative of the vector L with respect to the scalar s, which is the length coordinate along that particular line, in a making it a little more complicated to bring it on a planar curve. Then we will, in today's class, and to some extent we have done it already also, we will go out of the plane of the board also, make it a spatial curve. In all 3 cases, you see that a particle's motion, the most generic motion, this is the simplest, next simple on the plane, now out of the plane as well. So all motions can be expressed in terms of just this particular position s of t that you have. So it's a scalar measure number of what is happening on that curve. Okay. So whenever you're taking a derivative, and here again I should put an I over here. Okay. So whether I'm writing it in full like d by ds, or I'm writing it as a prime or a dot, I should mention, as long as what quantity whose derivative I'm taking is a vector, I have to always mention this frame of reference with respect to which I take this. Simple problems where you do not have any thing related to the frame of reference mentioned, just do this. Okay, always draw this. It might look superfluous, but this practice will help you in the long run for more complex problems. Okay, so this is L prime. Now, on the other hand, your L dot with respect to the same frame of reference will be defined as I dl by dt. Okay, quite straightforward. I'm only replacing s with t and a prime with a dot. Okay, but the reason I wrote it, even though they look very similar, is these 2 guys are related. The left hand sides are related. Can you say what would be the relationship between them?
They should be related by the derivative of s with respect to time.
Perfect, yeah. So which we'll call as s dot, right? So, and there I don't need to specify any frame of reference because s dot is just defined as ds by dt, and I'm using also ordinary derivatives because it's a function only of one independent variable. Okay, and even here I'm using ordinary because L is a function only of s, and s in turn is a function only of t. Okay, so implicitly L is also a function of time, but it's only through s, and therefore I can still use ordinary derivatives like what I'm doing over here. Okay, so if I know this as you said, so what would prime be in terms of the dot? So if I want to relate these 2 guys, which is I L prime to L dot with respect to I, what would I have to do with S dot?
You could multiply L prime by S dot, or divide
Very
the
good.
right side
Yeah.
by
Perfect.
S dot.
Perfect. Okay. because ds by dt, and this is as a dl by ds. The ds cancels. You see this is dl by dt, which is what you have on this side. Okay, perfect. Yeah.
Why
Good.
is the frame of reference not necessary to specify for the derivative of s or s naught?
Because it's a scalar quantity.
Ah.
Say s is just the arc length, right? So it's any measure number or scalar quantity that you have, it has only magnitude, not direction. Only when direction is involved, the frame of reference becomes important. Okay, next question. Oh, I would like you guys to use this microphone. I forgot to mention to you that. Yeah.
You want to start? Yeah. So we did include a frame of reference this time. You'll see it's much like the one that you have, where we define the frame of reference as I for standing for inertial, because we're not given a specific context in which the problem takes place. And so we're given in this question the velocity vector, and we're asked for the magnitude of acceleration. So given that we're given velocity, we know that we're going to have to take a derivative in order to get the acceleration. And so we defined acceleration as the derivative of velocity with respect to our reference frame I. And so in order to do this, since we're split, it's a vector, we have to end up doing chain rule, where you'll see this first term, v naught e negative t over t to tau times sine omega t, splits up into two terms, where first we take the derivative of this first portion here, and that's how we bring down the negative 1 over tau. That's the first part of the chain rule. For the second part, we take the derivative of the sine omega t, where the omega t comes out, and because we're changing from sine to cosine, it flips the sign. We do the same thing for the j component, where we have the same sort of chain rule. We'll see where negative 1 over tau comes out in front, and then when we're taking the derivative of the second part of cosine omega t, it becomes sine. It becomes sine, and the negative comes out, or the sign flips here. And so knowing that, we can further simplify the problem by just taking out a common factor, just to make it easier to plug in numbers so we avoid any mistakes. And by plugging in all these values, we can solve what the acceleration vector is. But then once we have the acceleration vector, what we have to do in order to find the magnitude is take the square root and square both components. And that's how we get 4.8. In addition, we also did this in MATLAB just to check our answer and show the equations are right.
All right, so I guess I can come over to this side. So we use the symbolic toolbox in MATLAB in order to first identify some variables that we can use in our equation without defining them first. So we have our velocity equation, which we just pulled from here, and we use it as a vector, and then we use the differentiation function in order to find the acceleration. And you can see these are the results of that differentiation. And there's no comma here just because MATLAB doesn't include that, but these are two different equations for the x and y components. And then we use the given values in order to substitute into these symbolic variables. And we find we use the subs function to find the substituting of these variables into the acceleration equation. And then we use the double function, which just converts it into a numerical answer, because this will actually just leave it in like sines and cosines, and that's not very useful for our applications. We want to find the number so we can find an acceleration. And then we use the norm function in order to find the magnitude of the x and y component of the vector, and we can see our answers match up to what we calculated by our hand calcs.
Okay, really appreciate that. Some of the good points that I would like others to note for their own things is one of the things they've done is to use the nesting appropriately in terms of the brackets whenever they have multiple brackets coming within each other. So that has been done appropriately. It's okay to skip in between any one of those kinds of brackets, but just make sure that the outer and the inner are in the same sequence. Okay. The other important thing that Nafis has done over here too, which is a good practice, is to mention either orally or in writing what is the rule or whatever you're taking in order to move from one aspect to the other. I really appreciate, Andrew, that you went one step ahead and tried to replicate whatever was done by hand, also by using a MATLAB code, because this is how eventually more complex problems will anyway be solved when you have more number of degrees of freedom and much larger sized problems. So getting accustomed to it for simple problems like this, which you could still do by hand, gives you a parallel, and that approach will help you in the long run. Thank you.
Can I ask a question?
Yeah, please.
So you know how if we take a derivative, we mentioned that it's with respect to the I reference frame. Do we carry that reference frame subscript into the acceleration, into the velocity at all? Can we continue that, or we just leave it off?
Yeah, it's okay to leave it because you have now defined this, okay? So you have defined A as acceleration in the inertial frame. So once you have done that, you can, it's understood, okay? Yeah. If you had not, if you had it more like, let's say in this I had put an I, then I should have continued. Because if I was interested, let's say in acceleration in I, acceleration in E, acceleration S, many different frames, then I would want to distinguish them. Here, it's appropriate for you, but just that, of course, there's a missing underline there, which is because it's also a vector. Then the rest follows. Yeah. Anybody else? Any question on this problem or the solution? Thank you. Next.
Hello, you want to come? Help me present? Okay, this is. Wait, what's your nose? Cool. You want to write it out?
Yeah.
I can walk through it. Okay. Okay, so this is our question. It's about a car traveling on a straight road. And so first, we should be drawing our frame of reference, which I did right up here.
Oh, sorry, I did not look.
So I simplified this to only having one axis, one just like an x-axis.
Yeah. You want to show it? Set.
So
That's isn't one axis reference frame to the Earth.
yes, so we're in the Earth's reference frame, and then this is our coordinate system. Our velocity given is 60 miles per hour, which that is 88 feet per second. Do you want to
Correct.
continue?
Yes.
Writing out my work. Okay, and so then A1 is given as a deceleration of 5.2 feet per second squared. And so since it's a deceleration, we're having that negative, meaning it's acting to the left based on our coordinate system. And then immediately after that deceleration, there's a second acceleration of 2.3 feet per second squared. And that's an acceleration, so positive and to the right. And so this is where our velocity final, because the question asked when it will return to its original velocity, is the same as our velocity initial, which is that 60 miles per hour or that 88 feet per second. So first, we're going to take the integral of the first acceleration with respect to time from 0 to t1, t1 being the 3 seconds, because you apply the brakes for 3 seconds, which if you write it in like the kinematic form, you're going to get that v initial plus a delta t is equal to the v2. And so you plug in those numbers. And so after the deceleration, your velocity is going to be 72.4 feet per second, and that's positive, so it's to the right. And it should have a nice little vector symbol over it, I think, all the
Do
velocities.
you mind if I erase the front part? Because there's more.
Yeah, it's okay, but she had a question for you.
Oh, I think we need to write the e's here, and then have little. These are all vectors, so they all need little symbols.
Yeah.
But
I thought that was. Right.
the velocities as well.
We would like to use the hatted quantities just for the unit vectors. So
Okay.
it's better that you use an underline
Okay.
or a vector on top. Yeah.
I did the underline first, but then I was like, no.
Okay, well,
So the underline is not for the subscript, only for the A.
1 second. Yeah.
Yeah.
Right. This is how I read it. Underneath.
No,
it's an
if-
underline underneath or an
if
arrow on
it's-
top.
Yeah, exactly.
Sorry,
So
what?
either an underline alone
Oh, okay.
or an arrow on the top.
So it's like, that's
Oh,
how I
okay,
like to
I see.
do mine.
Yeah.
No, because what I used to do is do it on the bottom too. My professor used to do it
Okay,
on the
yeah,
bottom.
it's just a question of notation, so as
Yeah,
long
yeah.
as you're consistent with it, that's fine. But once you put this vector on the left, you have to also mention the unit vector on the right. So you remember you introduced an E, you should also introduce a vector I hat
Okay.
along that path. Yeah. So where you have minus to plus, there you have written on the top,
Mm-hmm.
that sketch that you have done on the top.
Yes.
Yeah,
Yeah.
mark unit vector I on that, parallel to
Yeah,
the
right.
path.
Yeah. The,
Anywhere, doesn't matter.
Yeah.
But it has to be parallel to that.
I hat.
Yes.
Yeah.
That's, it's a I hat
Oh,
because
I
it's a
see,
unit
yeah.
vector.
I messed it up. My bad. Yes.
Okay,
This is.
so now I think we continue to the
So now
second.
you have to put an I hat on each one of those things.
Yeah, pretty much.
Because, yeah.
Yeah. This, yeah.
Those, so that VI is
It's
saying
not a
it's the
subscript, it's
initial.
multiplying that.
Yeah, so you have to multiply VI by I hat.
V times I hat.
This VI is meaning V initial.
Yeah.
Yeah, it's not on the left hand side because you already have a vector on the left hand side, that is V. Right? So it's on the right hand side where you do not have the vectors.
Correct?
I think he's
No.
meaning when you have the numerical answer, you
Yeah.
need the I hat. So it's not, is when we have like the little arrow on top, it like implies the I hat.
Yes.
Yeah, see, there are two things here. One is the vector, the other is the vector's measure number. So, see, you already have a vector over here. V is the vector.
Correct.
So now you
Yeah.
don't have an I hat over here. Okay, V hat is equal to whatever quantity you're writing.
Yes.
That will be in turn multiplied by I hat.
Correct.
To make the right, both your left hand side and the right hand side a
Oh,
vector.
yeah. So
Okay?
it has
So
to
there's
be,
no,
yeah.
no I
need-
hat
yeah.
over here on this
Yeah,
side.
makes sense. Okay. No, I was
Similarly-
getting confused here too. Yeah.
Here you would have I
Yeah.
hat
Yep.
and, yeah,
Understand.
yeah,
And then.
all of
Yeah.
that, yeah.
Okay, now for the second part of the question where after it decelerates, it immediately accelerates. So then we're going to take another integral of the second acceleration, which is that 2.3 feet per second squared in the I hat, positive I hat direction. And we're going to do that in respect to time 1 to time 2.
One second.
Not in respect to velocity. I think I might have wrote my notes wrong on that one,
Oh, okay.
but it's respect from time 1 to time 2.
I see.
And time 2 is our unknown, but we know that our velocity final should be the 88 feet per second. And so we can rearrange this similar to our top equation.
And then you get delta T was.
At 6.78
Seconds.
seconds.
Okay, brownie points for you guys for using a cute little car over there. The other thing is mentioning the reference for that as well. But a few things that I would like to point out for improvement in the next time. is subscripts are typically used to refer to components or measure numbers along those respective directions. If you have I, J, K, it would be 1, 2, 3 corresponding to each one of them respectively. So when you want to mention this is at T1 or T2, you put it as within brackets. So instead of putting it as 1 here, you put it as within bracket at T1, okay? Or if you want to use a simple notation, maybe you could use the 1 as a superscript or whatever, not as a subscript, because that's typically reserved for the measure numbers or the components, okay? So these are the things, and the few things that I mentioned earlier as well. Just I would like everybody else to take note of that. Anybody else, any questions on this?
So I did a little different way.
Okay.
Where first I converted it
You
into.
can project it, maybe you can just, yeah, just.
Do you have an HDMI on your laptop?
Yeah.
You have it work?
Yes. I did not use the integrals at all. I did it in a much simpler way.
Okay.
There.
It's good whenever you know of alternate ways of doing it,
Yeah.
for you to present that like the previous team did as well.
Yeah, so-
And I also like this going in pairs, doing it as a team, so that way it really shows the teamwork that's going on. Good.
Yeah, so first of all, I converted whatever notations we had into feet per second, and then times 60, so we get 88 feet per second. So every answer is similar to this. It's just in a more simpler and a different way. So I get 88 feet per second, and then what I did was the car decelerates at 3 seconds. So I said deceleration equals initial speed minus deceleration rate times the time. So what I did then, 88 feet per second is our initial speed. Then we come down in 3 seconds at 5.2 feet per second squared. So then we get 72.4 feet per second squared. And then it was really easy that acceleration is equal to change in speed by acceleration rate. So 88 feet per second minus 72.4 feet per second. If you divide that by the acceleration rate, which is 2.3 feet per second, you get about the same answer.
Well, it's the same equation. You're deriving this from an integral.
Yeah.
So.
But yeah, pretty much. But.
Yeah. So the advantage of going through this kind of an approach is just you're using the rectilinear scalar quantities.
Yes.
So you don't need all these vectors and other things which are.
That's what I thought.
Just that.
Would be easier. Yes.
Yeah. So, but always remember that it's valid only when you have rectilinear motion and
Correct. I
the
understand.
constant acceleration. So, of course, it was piecewise constant here.
Yeah.
There was a deceleration and then an acceleration. So, it's piecewise constant between them.
Whose laptop had the slides? Mine. Okay. Did you just refresh it?
Yeah.
I'll refresh it.
Well, it's live now. As long as we just start presenting it again, I think.
Yeah.
Put it in there. That's good, right?
Yeah. Sure. I can.
So we're given that
I'll start writing some stuff.
okay. We're given that an automobile passes point P at a speed of 81 miles per hour. So we're given the initial speed in this problem, and we're also given the deceleration rate. We're also given that it's a function of time. So after 4.8 seconds, we're given the final speed. So, yeah. So drawing out a diagram, it's on a horizontal axis of motion. We chose that reference frame, and yeah, just going on the x-axis.
And we're saying that our reference frame is with respect to Earth or the road. In this case, the Earth itself isn't specifically relevant to the problem. We're not considering gravity or anything. But it provides a good fixed inertial reference frame for our derivation. So we know that we're given an acceleration, but it's a function of time. It's not a constant acceleration. So that means that we're going to need to use an integral to accumulate the distance that it travels over time. And then the first thing that we did when approaching this problem was to convert the speeds from miles per hour to feet per second, because we're given the amount of seconds that it traveled and we're trying to find the amount of feet that it traveled, so we need to do that conversion. If you can write that on the board, that would be helpful.
Yeah. Wait.
Then converting these to feet per second.
Oh yeah.
And then the next thing we did was we defined our acceleration, which is one of the things that we're given in the problem. We don't know the rate that it is decelerating at, but we do know that it's proportional to time. So we can say that our acceleration vector is equal to some constant k times vt. And acceleration is a function of time, it is not a constant. We also know that our acceleration is equal to the time derivative of our velocity vector with respect to the Earth reference frame. And we also know that the acceleration vector is the second time derivative of our position vector with respect to the Earth reference frame. So if we integrate our acceleration with respect to time 2 times, we should be able to come up with a function that tells us what distance we've traveled based on the amount of time that has elapsed. So when we do this, we can take our indefinite integral, and then we get a constant of integration, which is our initial velocity. And we know our initial velocity here is equal to this feet per second,
but
we'll just leave it here in its symbolic form, just to simplify things. Then if we integrate this expression again,
There you go. Yeah.
A little confusing. We get a second constant of integration, which is our initial position, which we can call s at 0. But because we've defined our origin at the point P, which is where the problem starts, we can say that this is equal to 0. So next, we know that this is our function for s. We're also given another point that we know this function must satisfy, which is at time equals 4.8 seconds, we know that the velocity,
77.7.
we know that this equation, we know that the velocity of or speed of the car is this. So we can take our function for, I suppose, all this is missing the proper vector notation. So if we know that our v at 4.8 seconds is equal to 77.73 feet per second, and we know that this is given by our expression for velocity, which we found by integrating. So we can plug in, I guess before we plug in these values, we can solve symbolically. And we know we want to solve for our constant k because that's the only thing that we don't know about our expression for position. So if we say that our v at our final time, or rather v at 4.8 seconds is equal to k times 4.8
over 2
seconds squared over 2 plus our initial velocity, which is given here. We can solve for k, and this, wait, hold on. This is a 118.8 number. Then if we solve for our k value by subtracting 118, multiplying by 2, and dividing by 4.8 squared. We calculate, let's see, calculate a k value of negative 3.565 feet per seconds cubed. And then now we have everything we need to use our position function to find the distance traveled. So we know, you
Here.
can write it out.
Yeah.
We know that our time, where we're trying to find the distance traveled, is 4.8 seconds. We know that our constant, it's 3.565.
Oh, my bad.
Yeah. And then we're dividing by 6, multiply by the time cubed. And we have our initial velocity, which was given at 118.8 feet per second.
Well, S naught, which is 0.
And our S naught is 0. And so once we plug in all these values, when we take a look at the units as well, our constant value is in feet per seconds cubed, and we're multiplying by seconds cubed, so that becomes feet, which is what we want. And then this initial velocity is given in feet per second because of our unit conversions here, and we're multiplying by the amount of seconds, so that gives us a distance, which is the overall displacement that we want.
And then S naught is in feet anyways.
And S naught would be in feet, but it's also 0 in this case, so we do not care about it because where we set our origin. Once you multiply all these numbers out, then we get a final answer of 504.53 feet.
Okay, that's good. Just a few things. I would like you to be a little more elegant in your derivation.
Yeah.
As an afterthought, you brought this, but even now, the right-hand side is a scalar, looking
Yes.
like a scalar. The left-hand side is a vector. So you can just put it as magnitude over here.
Yeah.
We just put all of these as magnitudes, so that because that's all that you're really interested in over here. So that should be reasonably good. Yeah.
All right.
Yeah, and also, this t also you're substituting
Yeah.
there, right? Just
Yeah.
like how you're doing it over here,
Yeah.
right? So you'll have to be consistent. When you substitute in all the terms,
Yes.
not leave
Yeah.
t alone in the other terms. But the process is pretty much okay. Okay, thank you. Anybody any questions for them? Or okay, go ahead. Next.
So we had part B, question 1, and so I'm going to first go over the question. So we were tasked with calculating the acceleration in the x direction at time equals 1 second. And so we're only going to look at x equals r naught cosine angular and times t. So for deriving it, so we have, it's really hard to see, but those are little i's. So we have x in respect to I as the reference frame, it's inertia. And we're only focused on the x coordinates, so that's why we have I hat up here. So we start with taking the derivative of x with respect to I, and we get the velocity, which is also in respect to I. So this is the negative r naught omega sine omega t in the I hat direction. And furthermore, we need to get to acceleration, so we have to derive it once more. So we get the velocity derived, which gives us acceleration, which is in the after the derivative is negative r naught omega squared cosine omega t in the I direction. And when plugging in the numbers that we were given over here, r naught is equal to 6 meters, which we have here. We have omega is the 5.28 radians per second, and that is squared. We have cosine times the omega again times time equals 1. And so in the end, we get negative 63.70 radians squared per meter second squared in the I hat direction. And then Andrew's going to talk more about MATLAB.
Yeah, so we also coded this problem I kind of talked about using sims, so I'll just kind of go over it briefly. So we have the position equation, and then we just differentiate it to get velocity, and then differentiate it to get acceleration, and then we substitute the values, and we can see that all of our answers in the hand calcs section has been validated here symbolically, and then as well as our numerical answer. And this is just like substituting the variables into the acceleration and then converting it to a numerical answer.
And then one more thing to add, we did put a citation, but it must have gotten chopped off. This is from Google Slides.
Good, yeah.
I do have one question.
Yes, please. Yeah.
So when squaring radians per second, is it correct to have radians squared?
Yeah, I was
over
going to
second
talk
squared?
about it.
Okay, that's what I was.
It with your
I was a
question.
little iffy
So,
about that.
Radians is non-dimensional quantity.
Okay.
So you can drop that off. So the actual unit for acceleration is meter per second squared, which is what you already have. So the for completeness, what you have done is absolutely appropriate because you just borrowed it from the previous line of the equation. But then you drop that off. Whenever it's multiplying certain other things, for example, when it's angular velocity, you would continue to retain the radian as radian per second. Okay. But this, is like a translational acceleration, which is just in meter per second squared. So you just drop off the radians. Okay.
Okay.
So all angles, for that matter, are essentially non-dimensional quantities, and you can drop them off when you need to.
Okay, thank you.
Anybody else? Any questions on this? Okay, thank you. So once again, I appreciate the alternate methodology with the MATLAB code. Yeah. And the picture really illustrates quite a bit, so it's nice. Thanks. The video of
We thought it was a good representation.
All right, so we had a similar problem to the last question, but this time we're looking to find the acceleration along a specific direction vector. So we defined our reference frame to be a generic inertial reference frame, and we have our coordinate unit vectors. We have our x measure number and our I hat vector pointing to the right, and our y measure number and our j hat unit vector pointing upwards. You can see in the first quadrant of the graph there, we were just showing an example of where this rotating crank could be and where the pin could be at a given time. We're told that the radius is 14 meters, the length of the crankshaft, and that it's moving with a positive angular velocity, so counterclockwise. We also calculated, just to get an idea before we did the math, where the pendulum, or where the rotating crank was at time equals 3.8 seconds, and we can see that it is pointing downwards. If you look at the diagram shown in the top right, we can see the point. I know it's a little blurry, and we know because from our physics understanding that it is moving in a circular motion at a constant angular velocity, so the acceleration should be pointing inwards towards the center of the circle, which you can see as the vector pointing mostly up but a little bit to the right. We've also drawn the direction vector that we're trying to find the acceleration in, which is 0.6 I hat plus 0.8 j hat. We can call that vector L. To approach this problem, our idea was to find the second derivative of the position function that we're given, because that is the second time derivative is the acceleration, and then we can find the component of that vector onto the direction vector that we're asked to find the acceleration along. So you can see a diagram in the middle right is showing how to find a component vector. We want to find the component of the acceleration onto the direction vector, and the way we find that is by dotting the acceleration vector with the direction vector and dividing by the magnitude of the direction vector. In this case, our direction vector is given as a unit vector, so it only has a magnitude of 1, and we can just simplify it to take the dot product of acceleration with the direction vector. As Nafez is showing on the board, we take our position for x and y, and we write it as a single vector with our components I hat and j hat. Then we take the first time derivative. As you can see here, the omega symbol comes out as we take the derivative of sine, or take the derivative of cosine. end up with negative sign of the original, and then we have to take the chain rule, so there's an additional omega that comes out front. That's the same for the right term, except because we're taking the derivative of sine and turning it to cosine, there is no negative. We take the second derivative of position, or the time derivative of velocity, and then we get our acceleration vector. We see that another omega comes out much in the same way, and then this time both terms are negative because the left term is taking the derivative of sine and the right term is taking the derivative of cosine. Then we take our acceleration vector evaluated at time equals 3.8, and we dot it with the unit vector that we're given. We come out with a scalar value of 100.7 meters per second squared. You can see that the units here, yeah.
It's radians per second here times r's and cosine is just going to be what units?
So in here we have our angular velocity, which is in radians per second, and we're multiplying it by a time. So that ends up being unitless, which is good because we're taking the sine of that. And then we're multiplying by the radius. So we get meters, and then our angular velocity here is radians per second. And the radians is unitless, so we can say meters per second, which is good because we're trying to find a velocity. In this case, this term works out much the same to be meters, and then here we have per second squared, or radian squared per second squared. So we get meters per second squared, which is the correct units for our linear acceleration. When we multiply by this unitless vector here, then we end up with units of meters per second squared, which is an acceleration.
And the whole reason to do the dot product was to find a vector that was, or not a vector, to find the component of the acceleration that was acting in the same direction of 0.6i plus 0.8j. And you can see we also did this in MATLAB, where first we defined what the unit vector was. I put it as u, where it's 0.6i, where the first column is I, and the second column is the j component. Similarly, we have the x and the y written out, which we put into what I call the s as position. So this is the x component, this is the y component. We did the same thing where we take the derivative twice. First derivative, you'll see it lines up, and the second derivative also lines up, and then we substitute in the numbers using the subs function, and double in order to turn it into numerical quantity.
Okay, good job. I really like the due diligence you have given to all the vectorial quantities and other things. Just one suggestion, we use S as the arc length, so which is typically used as a scalar quantity. So I would prefer you to use in the future the symbol R for the position vector, or P, even P for the position
R
vector.
if they give us R naught? They give us R naught, and I don't know.
Okay. That's fine. That's a different scalar quantity that is over there.
Okay.
You could use probably P or something else. Okay, but S is kind of reserved, just like V is reserved for velocity, or A for acceleration, alpha for angular acceleration, omega for angular velocity, etc. Just to avoid confusion in the future,
Okay.
You can use P or any, even R for that matter.
Okay.
You're saying, what you're saying is right. Since you have an R, maybe you choose a P of T over there. In which case you can have this also as a vector, and this equation will be right because the right hand side is a vector, but the left hand side is written as if it's a scalar. But now you would have a, you would call it P and have that. Yeah. Okay. So anybody has any questions on this problem? Okay, let's move to the next step. So one more thing I'd like others to learn from the previous team is in terms of how you write because there's a camera which is recording, while the others in the audience can bend and see. If you're covering the whole thing, then nobody can see it over there. So just make sure you just move out and see, just like how the previous team did it. Yeah.
Sure, I'll stand in the middle.
Can I get your wrist?
Yeah.
So, the question we did was one of the Falcon 9 questions. So, given a two-stage launch vehicle which has a couple of known values, not all of them which we actually need to use, but yes. Yeah, so we'll just go through the ones that we do actually need to use. So we're given this expression for acceleration with respect to time. I'll just write that here.
Frame of reference would be also, because this is a two-stage rocket taking off, so it would be majority in the, if you see in the y direction going up, that would be the frame of reference. And after, it's like we are given certain amount of stuff in the equation, not all of it we will use. So after we integrate a value of t and use all the values that are given and plug it in, where t is 750 kilonewtons, m naught is 550,000 kilograms, m dot is 2,500 kilograms, and gravity, which is 9.81. So if you see here, where it has already been and then it has to be multiplied with 9.81. So that would give us the first part where it has been multiplied with 2,500 times 9.81 times t, which gives us 24,525 t. That would be our final equation after we plug in all the numbers and multiply it. Then we finally have to do integration of the equation to find velocity with respect to time, where we have sub-values where we switch, where
Yeah, that's so. I mean, I'll just finish writing down all the givens.
Okay.
The interesting thing was that the 160 seconds was not really needed.
Yes.
So that was a bit of extra information, but I think that's okay.
So this.
Our T is 130 more seconds, so we're resolving more.
Yes.
So
Yeah.
when we wanted, so first we would need to put in all of our nodes into the
There's that already.
Yeah.
So we are on the integration part. So we have the equation here. We won't take the time to write it because it's very long. So we'll take that as a reference of.
Do I need to? I don't know.
Yes. Do the integration part.
Okay, yeah. So, with respect to I, so there are sort of frame of references here, because we're only concerned with the vertical
Yes.
height and like vertical motion, we just took the y-axis to be our frame of reference. So integrating with respect to time in that frame, we get
From 0 to t. So, alright, that integration is there.
Oh, it's there, okay.
Yeah, it's there. Okay. So, yeah, you just need to write this part. But yeah, as you can see, that would be the integration part of that. Then we would need to sub in the values of u there. Our final equation of integration would come out to be just the equation.
Yeah. So then we would get
dy of t, yes, equal to minus 1 by 2,500. In the parentheses, 2,104,500. Zero to t.
It's a long number.
It's right.
Yeah.
Fine. So 0 to t,
0 to t.
1 by u dl, plus.
By u.
So after breaking this down into ay and parts of t, you'll have to we'll get this as our final integration. 0 to t by u du.
T by u.
Yes. So this would be our final integration, and now we can start solving this integration in first and second term. So after solving the first term of the equation, we would get dy of t equals minus 841.8 and of modulus 550,000 minus 2500 t. This is what we would get after the first term. And after we solve the second term of integral, we will also get our final number to be
Our final number.
would be dy of t equals
That's
plus 9.81. Yeah. All right. Yeah. This would be the final number after the second term equation 2. And now we have to find y of t. So we have to integrate this even once more. So it would be y of t equals 0 to t dy of t.
yeah.
And we would put this in the equation where our final integration would come out. If you plug it into numbers, it's just
Plug in, it's just the integration of this over from 0 to t.
Yeah.
I'm not gonna write that.
yeah, it's pretty long again.
It's pretty long.
But then after that, we are given time, so now we can easily find time at 134 seconds what it would be. So if we write that integration of y equals 0 to 134,
y of 134
before,
is equal to
yeah,
0 to
134
134
yeah,
of v y t
d,
t,
yeah,
and then
equals 71591.5155 meters.
yeah, and
So
then
which
we
would
can
equal-
convert that to kilometers because that's what the question asks.
Yeah, and that's what the question asks. So we'll get 71.5915 kilometers. Yeah.
All right. Whatever the equation is given there, it's a fairly straightforward, simple equation based on Newton's second law. Can you reason out what is the significance of that? How do you arrive at that equation? Though it's not a part of the question or problem, just an additional thought.
I think if we were to draw
First you start with Newton's second law. What does it
F equals
state?
ma.
Yeah.
Newton's second
So
law.
in this case, what are F, M, and A is what you have to look at.
So I mean, I'm thinking about it like if we have the rocket,
Mm-hmm.
and if we take a look at like the forces that are acting on the rocket,
Yes.
it has a force of gravity because there's a mass
Yeah.
on the rocket.
Yeah.
That is
There's
There's
also
thrust.
there's also the thrust,
yes.
which would be going.
So if you imagine what I kind of imagine is it's kind of like going up, where thrust is going up, where
Mhm.
other like forces are pointing down. Like if you see M not G
Mhm.
down.
This is the m naught times.
Yeah.
Well, it's we would also need to multiply by t.
T. Correct.
So those are essentially, I think the three forces that are
Mhm,
acting on
mhm,
it.
mhm.
So if we were to, I guess, solve, and we know that the system is accelerating.
Yeah.
So if we have like, I guess, some m times AYT.
So your M is also a function of time, right? Because of what is happening
Right.
to the propeller.
So I guess we could, and would they both be within the same like reference? Would
Mm-hmm.
okay. I guess that would be equal to the thrust minus.
Minus.
So you don't need to put the I for the scalar quantities like
Okay.
mass. Yeah.
I see. So my question is this not a scalar? Is this a scalar?
It's a
quantity?
scalar equation because you've given only one measure number AY. If you give AX, I
Oh, I see.
plus AY, J
Okay,
plus
okay.
A.
So none of these expressions would need
It would, because see, you'd still have a particular frame of reference with respect to which those measure numbers or components are taken. Okay, before they get into the equation, you have to do it with respect to a particular frame of reference. Okay, you could have alternately chosen some other, let's say, an oblique frame of reference, which doesn't have the vertical direction, but it had some two directions which are making a certain angle to the vertical. Then you will have components along both. So in which case you would have had to write it as a vector equation. Right?
So
Yeah, that would be t minus m naught j plus mgt.
well, this is also going down, right? So it would be, or is it plus? Oh, okay. I guess it is.
Yes.
Yeah. Okay.
GTS. Yeah, pretty much.
And
So essentially it's thrust minus the weight, right?
Yes.
And
yeah.
the weight
So-
is a function of time.
correct.
So you have to,
So
the weight
that
is
what I was
the
trying-
original weight minus the whatever propellant is
Yeah,
burnt
so
out.
first the numerator is the thrust going up and the force is acting
Yeah.
downwards, whereas the second denominator part of the equation is the weight that is pulling it down and it's
Exactly.
going through. That is what
so this term
should be
is
equal to that.
essentially
Would
the
be the
weight of
force,
the fuel,
Correct, yeah.
yes.
and that's
Yeah.
decreasing with time. So this
Okay.
expression would be the function of the mass.
Yes.
So yeah.
Okay, good job.
Yeah. Wait, sorry, the slide didn't update.
You also
I did
mentioned
add
about
minutes.
a lot of data not being utilized because this is going to be a continuing question for a few other problems. So some of them might require that data. That's one thing. The other, of course, is typically
like, why have they given this? I don't understand why.
right. No, sometimes.
There must be some use of
Yeah.
it, else they would not give it to us, right?
No, but that's how the reality is. There's so much of a data, amount of data that we have access to is so much more than what we need for any particular problem. So we have to pick and choose what is the appropriate data to solve a particular problem.
Okay, so we have a very similar question where our first part we have the same equation, same initial values, and we have that t equals 134. So I'm just going to steal VT's work of writing it all out. But for this one, after 60 seconds, it turns 45 degrees and then accelerates sideways. So we're going to have both a y and x component of acceleration. And so you have to have both I hat and j hat. And so I drew a little diagram of how it'll like go up for the first part and then to the right for the second part. And so I approached this problem by splitting it into two parts. So the first one would be that for 60 seconds would be the integral of that a y of t. I did a little subscript 1 from 0 to 60, and that's going to get us our velocity 1 of t in the I hat direction. And I just put, I guess this is where I think the first error could have come in first error I encountered was that this is in kilonewtons. They converted it to newtons and then got their answer in meters. I decided instead I'd have these in megagrams, which is a metric ton, but I like to call it megagram instead, so I use for these numbers 550 and 2.5. Yeah, megagrams. So
Per second.
for that one, yeah. And so then after getting that out, this would be in the j hat, my bad. This is going to be equal to 0.367 kilometers per second. And so then for the second part, it changes up a little bit where our a of x is going to be t over the square root of 2 and then divided by the same like m minus m dot t. So integrating that second part I messed up on, you have to do it from 60 to 134, and that will help like include the mass has already like, because at this point
Make
the
sure
mass,
what you are integrating with respect to a of x times.
dt.
yeah, so that would help the mass flow rate, because at this point the mass is decreased to only 400,000 kilograms or 400 megagrams. So taking the integral of this is the x component, I get 1.316 kilometers per second, and then have to do the same thing for the y. And out of that, I get 0.591 kilometers per second. And so then I have to take the magnitude because I want the total velocity. And so I add this 0.591 with my original 0.367. And I didn't write that number down, but it was around 0.9-ish. And then that squared plus the 1.316 squared, square rooted, is equal to the 1.628. That'd be kilometers per second.
Yeah. So probably should have started off with this, but the basic premise of the problem is that we're trying to basically use the acceleration function that they gave in the beginning, take the integral of that, since the integral of acceleration is velocity. We find the initial velocity after the first 60 seconds that it's going straight upright. So that's the, like, I guess, when I was doing the numbers, we called it v1y, so it's like the first velocity and it's only in the y direction. But then in the second part, like the second stage, when it tilts 45 degrees, we have a v2y, which is in the second velocity, the y component of that, and then the y component in the x direction. So then taking the integral of acceleration in both the x and y directions, as you can see here, and also taking into account the time at which it's happening. Stage 1 is at 0 to 60 seconds, and then the second stage is 60 to 134. So we're taking the integral from 60 to 134 of the second two functions for v2y and v1y. And then adding the two components together, we get vy total, and then vx, and then we just do a Pythagorean theorem to find the total magnitude incorporating both the x and y directions. So that's just kind of like an overall walkthrough.
Okay, good. Should have made Elon Musk quite happy. There are certain things which are mentioned in terms of simplifying assumptions there. Do you see the role of each one of them? If they warrant which could change in your problem, for example, it says including constant gravity, for example.
So in higher altitudes, obviously the acceleration due to gravity will change a bit since you're farther away from Earth.
Yeah. Because the distances involved are fairly large. Right?
Yes.
So just like you're talking about megagrams, you might have to talk about megameters as well over there, right? So
yeah.
The change possibility is something which is appreciable. Unlike for, let's say, an aircraft cruising at about just 11 kilometers.
Yeah, there is
altitude,
also differences in pressure, which will change the effect in acceleration that the force will have on the spacecraft. And also, there's one other thing. Oh yeah, there's also a lot of pressure differences when you're going through the different levels of the atmosphere. There are different barriers that have to be crossed by the rocket, but those shocks aren't really taken into account in this problem. That's all simplified. We just pretend the atmosphere is a perfect gradient with very little change rather than layers.
One more assumption which is kind of specific to your problem is moving from the first stage to the second stage. When you're going vertical and then you're going at 45 degrees. Do you think that's possible so discreetly? So
No,
what exactly
No, it would
happen?
go up and then slow once the stage like pops off, and then it would kind of launch it again. I don't know how to explain it, but it's more of a parabolic thrust rather than a constant thrust.
We have our nice little sharp 45-degree turn right exactly.
Yeah.
Yeah.
You'd have thrust vectoring, so you'd actually gradually change the angle at which the propellant goes off after burning. So
Yeah.
the direction of the thrust will therefore change gradually. It will not be zero and immediately 45 degrees would gradually
Right,
change.
yeah.
So you will have in between those two straight lines, you'll have a curved path as well. Okay.
I guess in a perfect thruster, you could probably approximate the parabolic velocity vector as sort of like a constant linear one, and then in which case you would be able to add the magnitudes and get a relatively perfect approximation. But again, we have to assume that it's a perfect parabola where you have more thrust in the beginning, so a higher velocity at the beginning, you have a cruise at the top, and then it comes down before the second stage. We'd have to assume it's a perfect parabola.
Sure, sure. The same set of assumptions was for Tilak and Vitti too, the previous problem, right? So you guys can you think of the other assumptions you're talking about here other than constant gravity? Let's say, for example, what would happen if this was to be taken into account, aerodynamic drag?
Well,
What-
VT
what?
had her little rocket diagram, her little FBD up here, and so the drag would also be accelerating it downwards and working in the same way as gravity, and so you'd have to include that. And
So where would that come, in which equation?
so, I guess if it was you were doing the sum of forces, and that's how you got the T, you would have to subtract the drag as well.
Yeah, so remember they talked about how the numerator and denominator of that equation came up. So from Newton's second law. So your forces are all on the top. It's a net force, thrust minus the weight, but then you'll also have minus the drag, right? Perfect, yeah. What about the next one there? Thrust constant with altitude. Suppose it wasn't constant with altitude, what would happen?
I think that could go on. Well, if
Yeah,
thrust
it
wasn't
would-
constant, of course.
Yeah, if
Right.
thrust wasn't constant, then that would also affect the parabola I was initially talking about with velocity. Then there would be a new variable in that as well.
Yeah.
So the acceleration would be changing. So
Yeah.
I guess it would be a cubic function of some sort.
T
Yeah.
would have to be dependent on X
Perfect,
too.
yeah.
Yeah.
Y, or whatever.
Or Y,
Yeah. Yeah.
I guess my question in that scenario would be like, if T is with respect to X and all the other variables are with respect to Y, and we were trying to then find, velocity and then over the distance with respect to time.
Yeah.
Trying to take the integral back, how would that kind of?
Yeah, so that's the chain rule, right? So you have t as a function of s and s as a function of t. So you'll have to bring that in. So s of t is an unknown as yet, but it will become a part of your problem which you will eventually solve for. Okay, is that all that they have in the list? Yeah.
Dr. Dinesh, quick question.
Yeah.
If this was with respect to y and we knew the I guess that would be a different function. But if we knew the distance, couldn't we theoretically just integrate it with respect to t anyways, since it's a function of t?
Yeah, because y, remember, is also something, is a part of your dynamics problem.
Right.
That's
yeah.
also something you're solving, okay? Whereas this function t of y, exactly how it depends on y, will be given by the propulsion group.
Right.
So they know how the fuel burn rate is if in the propellant, if it's a solid propellant or if it's a liquid propellant. Based on that, they will give you certain equations, right?
Right.
So based on that, they could even give it as a function of time directly, in which
Yeah.
case you can
Then
just,
you don't have to integrate at all.
Exactly, right.
All right.
Thank you. Next. You're done?
That's
Okay.
it.
You have 3 more, right? No? That's it?
That's all we
Oh,
have.
okay. Okay, good. Should probably stop the recording and start again, yeah.